next speaker is Patrick Becker, who's working in Stephen Olmshank's research group at Denison, and he'll be discussing progress towards laser cooling barium ions.
Hello, I'm Patrick Becker. I'm working with Dr. Olmshank at Denison, as you said, and I'm going to talk to you all about laser cooling barium ions. So first I'm going to tell you a little bit about how we can use trapped and laser cooled ions for use in quantum information as quantum bits to replace conventional computers in some situations. Then we're going to talk about actually laser cooling them in the experimental apparatus and such. So first, quantum information. In order to understand quantum information, you have to understand regular information. So classically, in a normal computer, we store information in the form of bits. So that can usually be in the form of some electronic switch that's either up or down. So in case of like a light switch, for instance, turned on would be 1 and turned off would be 0. So long strings of those can constitute like a movie that you're watching, or like a Word document that you have saved on your computer, something like that. So a quantum bit is similar to a classical bit. It also stores information, but it doesn't store it in a switch necessarily. It stores it in the superposition of quantum states in some quantum system. So for instance, you can store information in the energy levels of an atom. So for instance, these are the hyperfine levels of a generic atom that I think this is actually barium, but I can't actually do that. So for instance, the F equals 1 state would correspond to a 0, and the F equals 2 state would correspond to a 1. The cool thing about quantum bits is that because the information is stored in superpositions, they can overlap each other, as long as you don't look at them, because then quantum states, they turn into just normal states, basically. So you can have either an on, which would be this state, and off, which would be that state, or anywhere in between. So you can essentially have an infinite number of different combinations saved in a quantum bit, which gives you a lot of different options for doing things if a quantum computer was to come to fruition finally. So yeah, for qubits, we're particularly interested in trapped and laser-cooled lanthanum ions. So in particular, doubly ionized lanthanum, that's lanthanum with 2 electrons knocked off, so it's positive. And this is a pretty excellent candidate for quantum information as a qubit, which is a quantum bit, because it's an ion, so it can be trapped in a potential well, like made of electric fields. It has a nuclear spin of I equals 7/2, which means that it has those hyperfine states that I told you about in the last section, so you can actually store information in it. And then lastly, it has a ground state transition that's stimulated by light at around 1410 nanometers. That's in the infrared and is actually very close to the wavelength that the current telecommunications industry uses for communication over fiber optic cabling. So in this chart, we can see attenuation through fiber optic cabling over wavelength. So attenuation is basically if you send a signal along it, how much it will degrade over time. So you can see that for 800 nanometers, which is pretty close to red, the attenuation is pretty high. But once you get closer to around 1400 or 1500 nanometers here, the attenuation is very low, which means that information can travel very easily through fiber optic cabling without having to be repeated. So that basically means we can spread quantum computation to the world, which is good. So there's an issue with lanthanum, and that's it hasn't really been studied much. Specifically, the hyperfine levels, we don't exactly know where they are, so those have to be measured. We're working on doing that in the lab as well, but first, we'd actually like to look at barium ions, barium-138. It's been laser-cooled before, and it's also very atomically similar to lanthanum. You can see that they're both right next to each other on the periodic table of elements. Barium is here and lanthanum is there, so they're atomically similar. They have similar masses as well, atomic masses. Barium has an atomic mass of 138 and lanthanum has an atomic mass of 139. This basically means that we can first trap barium ions in our apparatus and essentially test it out and characterize it to make it much easier to eventually trap and laser cool lanthanum. So for the rest of the talk, we're going to talk about barium because that's what we've been working on recently. So laser cooling is a way of confining atoms and ions in one location so that they don't have very much energy at all. With quantum information, it's important to completely isolate your qubit from external influences. So you can use light to cool down or reduce the velocity of individual particles. So there are a couple of cases here where an atom or an ion will actually absorb light that's incident on it. So if an atom, I'm just going to say atoms here, if an atom isn't moving, it'll absorb a wavelength or a frequency of f naught, if that's its transition frequency. And if that's the case, it will absorb the momentum of that light and start moving in the direction of the light. So if the atom was not moving, the light was going that way, and it would absorb it, the velocity of the particle would then be going in that same direction. But then, if the particle is already moving in this direction, and then light is incident on it, it will only absorb light that is slightly higher in frequency. Because according to the Doppler effect, that atom will see the light as being its transition frequency, which is good, so it'll absorb it. And if that's the case, it'll also absorb the momentum of the light, but since it's already going in this direction, it'll just be going faster in that direction when it absorbs it. Now the last case is if the atom is moving against the direction of propagation of light. Here the atom will absorb a redshifted photon or light. So that means that the frequency is slightly lower than the transition frequency. And in that case, when it's absorbed, the atom which was moving against the velocity or the direction of light will absorb the momentum going in the opposite direction and they'll cancel out partially. So in this case, the velocity is smaller than the original velocity. So laser cooling uses this bottom case here to slow down atoms and ions just by using light, which is pretty cool. So with barium, we can use this to cool barium down to about 500 microkelvin and lanthanum down to 1 microkelvin. And a microkelvin is 10 to the minus 6 or 1 millionth of a Kelvin. So that's pretty cool. All right, so in order to laser cool something, you have to have lasers at a proper frequency. So in order for barium to absorb, the frequency that we're going to be driving is this, this ground state transition from the 2s1/2 state to the 2p1/2 state. This would be driven by a transition at a 494-ish nanometers, which is a lovely blue color. So it's actually pretty much that blue color there. So once it's risen up to this energy level, about 2/3 of the time, it'll fall back down to the original level, and then we can pump it up again, and then pump it down again, and then pump it up again. And that cycle of it absorbing light and then emitting and absorbing more light will slow it down to that very low temperature that we said before. Sometimes, however, about 1/3 of the time, the light will actually fall into this other state, this 2d3/2 state. We don't really want that because it'll stay in that state for 80 seconds. That's the lifetime of this state before it decays. And in quantum mechanics land, that is an absurdly long time. That would break everything. We don't want that. So we have a second laser that's running at about 650 nanometers, that's just plain red, that will repump the atom or the ion back up to this p1/2 state so that it can fall back down here. So you can imagine that this cycle will go up, down, up, over here, back up again. Then do that some more, and then back over there, and such. So it'll continue cooling in that way. So a perk of an ion is that in addition to being laser cooled, it can also be trapped in a potential well basically made of electric fields. So that means that we can isolate and trap the particle in a roughly small space and then laser cool it to make it even less energetic. So the trap that we're using is a linear Paul trap that uses these 4 rods with different voltages on them. 2 of them are grounded, and then the other 2 here are an AC current, an RF field. We can oscillate a voltage across those at around like 40 megahertz. Basically, these rods will isolate the ions. These would be trapped ions in the X and Y plane, so this plane, and then these 2 end caps which both have positive voltages on them will isolate the ion in the Z direction. So they'll just hang out here for a while, and we can shoot the blue in from there, the red in from here to laser cool them. So here's an actual picture of the trap itself. So you can see the needles here, and then this is a 3D model of it. So you can see the rods there, and then these needles in between act as the end cap. So the ions will hang out right there. Okay, so here's another close-up of the trap. This is after it's already been completed, and then this is the whole apparatus. This is the vacuum chamber. The ions have to be trapped in very low pressure so that they don't get bashed into by like a hydrogen atom or something like that. All right, so now the lasers themselves. So we have two lab-built external cavity diode lasers that run at the two frequencies. Well, one frequency that we need, which is 650 nanometers, and then another runs at 987 nanometers. We use that to, we frequency double that laser with this second harmonic generation cavity to get the blue light that we need, because you can't actually get a laser that runs at that wavelength. So basically the way that this works is we feed the infrared, the 987 light, into this cavity, and once it gets inside, it bounces around all of these mirrors and builds up until there's a ton of power, about 4 watts, which is a lot higher than what we can actually produce just from our diode laser. Then when there's a sufficient amount of energy, once it passes through this crystal called a BIBO crystal, it will actually double its, or the crystal will absorb 2 photons and then release 1 photon of double the energy. So a bunch of blue light will shoot out of it. So here are our 2 external diode lasers, and then here's the second harmonic generation cavity. You can see nothing here because it's infrared and then it shoots out a bunch of blue light. So then the current status of the lab is that we have that blue light cavity locked. The vacuum chamber and all of the apparatus is completely built. We have an imaging system for actually looking at the ions, and we started attempting to trap ions earlier this month, but we've not quite gotten there. And so we're checking the wavelengths and the frequencies of those lasers just to make sure that we're at the right spot. So I'd like to thank Dr. Olmshank, my advisor, and also Zach Hewitt, who's my other lab mate this summer, and then other recent members, as well as the Army Research Office, Denison University, and the Anderson Foundation, the Research Corporation for Scientific Advancement. Thank you.
Okay, thank you, Patrick. Questions?
In your diagram, /back, I'm not entirely sure what, what the piezo, is that like a piezo speaker? Or?
Oh, sorry. Yeah, so a piezo in this case, the way a piezo speaker works is when you put a voltage across it, it expands and contracts a teeny bit. So the piezo here is between some like solid mount, the piezo, and then the mirror, so that putting a different voltage through it can like expand and slightly change the position of the mirror. Light will only get into this cavity if an exact integer of the wavelength of the light fits inside of it. So basically, there has to exist like a standing wave between all of these, and in order for that to happen, it has to be a very precise distance that the light would have to travel here. So we can change the position of this mirror ever so slightly to get this cavity exactly on resonance, as it's called, and then that's how we get the most light in and out and produce the most blue.
Okay.
Yeah.
You said you've tried to trap some of the atoms already.
Yes.
How can you tell when that's done? Like how I guess are you?
Oh yeah, okay. So even if you have an individual ion trapped, so when you're laser cooling, it absorbs light, but it also emits light, so it'll fluoresce. It'll glow blue, essentially. So we've designed a camera system. Well, we bought the camera and then we designed an imaging system to get a 54 times magnification, so that we can look in a window similar to this into the trap, and we'll essentially see a little glowing blue dot if there's an ion in there. That's how we know. Yeah.
So are you capturing those images with like a CCD camera or something? Or?
I think is it a CMOS or a CCD camera?
It's a CMOS.
Okay, it's a CMOS camera. Yeah. Mm-hmm.
Any other questions? Yeah, without.
How soon do you think we'll have quantum computers in the laboratories?
See, the thing with that, okay, so the main goal, let's say one of the primary motivations for building a quantum computer is to factor really big numbers, because that's something that classical computers just straight up can't do efficiently. Quantum computers can do it very efficiently. You can argue that maybe quantum computers already exist because there have already been examples of people factoring numbers like 15 and 24 with a quantum computer. The quantum computer is pretty big, right? So it'll be some time until we can factor numbers with like 40 digits. I'm going to say 2 to 80 years. So probably in our lifetime, maybe, hopefully.
Sounds good. It sounds like a fun discussion that we continue over lunch. So thank you.